presentation now and play it for every distinguished audiences.
Okay, sure. So wait, okay, sorry, sure. So let me introduce first. So our final speaker will be giving in video. So it will be the title will be on the performance of a probabilistic shaped 16 quantum with different entropies using a probabilistic aided maximum likelihood sequence detector. Okay, so you may
Yeah.
start the video now.
Okay, thank you.
We're not sure if we can hear your video. We can hear the audio.
Could you see the video?
We
When
can
you
see the
share
video.
your screen, you need to click share computer sound so that we can hear the voice.
你可能要重新共享一下吧。
OK，
就是你共享的时候，你要勾选共享电脑的声音，要不然我们就听不见。
OK。
In QAM with
Okay, now it's better. Okay, let's get started. 重新开始吧。
好的。
From Beijing University of Post and Telecommunications. The topic of my presentation is about on the performance of probabilistic shaped 16 QAM with different entropies using probability-aided maximum likelihood sequence detector. This is the outline of this presentation. First, I will give an introduction about the background. In this part, I will show the motivation of this paper. Then the principle of the proposed probability-aided MLSD will be shown. Next, the simulation and the experimental results will be demonstrated. Finally, I will conclude this presentation. Now turn to the first part, introduction. Here we give a picture to show the relationship between the achievable information rate and the signal-to-noise ratio under the given modulation format. From the picture, we can see that the probabilistic shaping technology could provide a higher achievable information rate, and it has been widely used in coherent optical communication systems. However, all the greater improvements have been achieved assisted by PS technology. Some adverse impacts of PS technology on the digital signal processing chain are emerging and are to be investigated, especially for those strongly shaped formats. According to the function of the models, we can divide the coherent optical communication systems into three parts. That's the transmitter side DSP, the link, and the receiver side DSP. In this presentation, we mainly focus on the receiver side DSP. As shown here, the receiver side DSP could be divided into the following parts according to their functions, including traumatic dispersion composition, clock recovery, equalizer, carrier recovery, design model, and the forward error correction decoder. We can see that as for the electric dispersion composition, equalizer, and the FEC decoder part, they are compatible with the PS technology as shown in the reference file. However, when it comes to the other parts, the adverse impacts of PS technology emerges unexpectedly, and various modified schemes are proposed and investigated to reduce the adverse impacts as possible. As for the symbol design model, although a probability-aided MAP scheme has some contributions on combating the adverse impacts of PS technology, there is still some performance penalties can be observed because the probability-aided MAP scheme only utilizes the noise variance to conduct symbol decisions, and it could not utilize the kinemagnetic field response. Thus, in order to investigate the impacts of PS technology on MLSD, a probability-aided maximum likelihood sequence detector scheme is investigated and proposed, and we will show that the proposed PMLSD schemes could utilize the noise frequency and the magnitude response simultaneously. After the introduction part, we will introduce the principle of PMLSD in the second part. First, we give two candle constellations following two distributions. the uniform distribution and the Maxwell Boltzmann distribution, and this kind of probabilistic shaping constellation could be obtained by the CCDM. The height of the bar represents the probability of the constellation points. You can see that in the right picture, the probabilities of different points are different. As a result, the decision threshold of the in-phase space or the Q-phase should be adjusted following the distribution, and this has been demonstrated in the picture. As demonstrated here, the probability density function of the in-phase space PAM4 signal or the 16 COM signals with different entropies are different. The black solid lines represent the PDF of the uniform distributed 16 COM signal, and the blue solid lines and the red solid lines represent the PDF of the PS1 signal and the PS2 signal, whose entropies are demonstrated here. Thus, the optimal decision threshold of the UD signal, PS1 signal, and the PS2 signal should be the black dashed lines, the blue dashed lines, and the red dashed lines of the red dashed lines respectively. Obviously, there will be some gaps between the three optimal decision thresholds, and it could be defined as an error-prone area labeled by EP in this figure. The gaps demonstrated here could be utilized to show the adverse impacts of PS technology on the digital model. Therefore, the VOD-based decision scheme is suboptimal in PS systems, and we need to explain a key parameter of the cost function of the traditional MLSD is the parameter HI. HI is the width of the parameter response filter. There are two popular ways to obtain this parameter. The first one is estimated from the training sequences, and the second one is estimated by the AR equations. And this way has been adopted by this paper. Based on the analysis above, a novel decision scheme should be investigated. And after the theoretical deductions, we can find that the optimal cost function should be modified into the equations as demonstrated here. The second term is the biggest difference between the probability AD, the MLSD, and the traditional MLSD. Aided by the offset term, the symbols located in the error-prone area could be decided more correctly, and better performance could be obtained. We will verify it by simulation and experiment as following. Next, we will demonstrate the simulation and experimental results. Based on our previous analysis, PMLSD mainly combats the enhanced embedded noise. Thus, aiming to analyze the performance of PMLSD, only the enhanced embedded noise are considered in the simulation platform. For clarifying conveniently, we use the original maximum likelihood sequence detector to represent the traditional MLSD scheme, and it is marked as OMLSD in this presentation. Therefore, the deployed three decision schemes in this presentation are direct decision schemes, recorded by OMLSD schemes, and recorded by PMLSD schemes, which are donated by without MLSD, with OMLSD, and with PMLSD respectively in this presentation. The simulation results are shown here, and the BER threshold has been marked by the red dashed lines in this figure. The improvements of PMLSD on the various PS signals with different entropies are demonstrated in the instead F. With the decrease of the entropy of PS signal, the performance improvement introduced by PMLSD with respect to OMLSD gets more obvious. This is based on the nature that the width of the error-prone area would be widened and more symbols would fall into this area. Thus, symbols located in the error-prone area would be decided more correctly aided by PMLSD, and the performance improvement would be correspondingly tend to be obvious. based on the simulation results, aiming to further investigate the performance of PMLSD. An optical back-to-back experiment is carried out, and the details will be introduced in the following part. First, the experimental setup is shown here. There are 3 kinds of PS signals are utilized whose entropies are demonstrated here. The corresponding experimental results are demonstrated in the right side. As shown in this page, different signal entropies contribute to different performance improvements of PMLSD. When it is deployed to a slightly PS system, such as the first one, there is a little OSR sensitivity improvement at the BER threshold. However, the OSR sensitivity improvement introduced by PMLSD becomes worse, and about 0.2 and 0.34 dB improvements could be required for the second and the third kind of PS signals as shown in the inset. There is a little differences between the simulation results and the experimental results because there is a simplified simulation platform utilized to evaluate the performance of PMLSD, in which only the enhanced embedded noise are considered as presented above. Within the allowable range of error, the experimental results are basically consistent with the simulation results, and we can draw the same conclusion that with the decrease of the entropy of PS signal, the corresponding performance improvement introduced by PMLSD will get more obvious. The trend verified by the experiment is consistent with that verified by simulation. Now let's have a summary about this presentation. In this presentation, the performance improvement of PMLSD is investigated by deploying various PS signals with different entropies. The contribution of this paper could be listed from 2 aspects. Firstly, PMLSD decision scheme could effectively alleviate some adverse impacts of PS technology on the decision model. And secondly, the corresponding improvement introduced by PMLSD is affected by the signal entropy. If it is deployed to a slightly probabilistic shaped system, the performance improvement is insignificant. However, if it is deployed in a strongly PS system, the performance improvement of PMLSD will tend to be significant. That's all. Thank you for your attention. And if you have any questions on my presentation, please feel free to contact me via my emails. Thank you.
No, it's nice. Yeah.
Okay, thank you, Xiaoshuo. Xiaoshuo, could you